Okay, so we're going to start off by graphing a line, and lucky for us, this is in slope-intercept form, which makes it pretty easy to graph, right? So we've done this before, the B, that's the y-intercept, so I'm going to start with that. So my line crosses the y-axis at -1, and then 2/3 is the slope, so from any point on the line I can go up 2 to the right 3, right? Rise over run, up 2 to the right 3, to find another point, or I could go down 2 to the left 3, that would work as well. And then you can connect the dots, and we got ourselves a beautiful line with a slope of 2/3 and a y-intercept. Well, it's not beautiful because I messed it up, but it's not too bad, I guess. All right, so there it is. All right, so let's move on to the next problem. So we're going to solve this system of equations by graphing. System just means we've got more than one equation. So what we really want to do is find the xy pair that satisfies both of these equations, okay? And we can solve this by graphing because if we have two lines that intersect, then the intersection is going to be an xy pair. That xy pair is going to be on both lines, and therefore it will satisfy both of the equations. Okay, so let's try graphing these. Now these aren't in a great format for graphing. I'd rather have them in y equals mx plus b form. So hey, let's put them in y equals mx plus b form. So I'm going to subtract 4x from both sides to get the y by itself. Okay, and I could say 2 minus 4x on the right side, but I'd rather slip the x term in front of the 2 so that it looks like this. Because now it's in y equals mx plus b form, right? And I'm going to do the same thing here. I'm going to subtract x from both sides. So that's going to give me negative y equals negative x plus 3. I put the x in front of that again. Okay, but I want it to be y equals forms, not negative y equals forms. So I'm going to multiply everything by -1. So then that becomes positive, this becomes positive, this becomes negative, okay? And now these two equations are a lot easier to graph, okay? So, hey, I'll graph this one in pencil. So my y-intercept there is 2, and my slope is -4. So I can think of that as -4 over 1, right? Down 4 to the right 1 puts me something like that. Okay, and then connect the dots. There's my line. And then I'll do this one in red just to differentiate them. Okay, so here my y-intercept is -3 and my slope is 1. So I can go up 1 to the right 1, up 1 to the right 1. I can do that all day if I like. Okay, and this method it works nicely if you happen to have an integer solution, and they're pretty simple lines. It's not a terrible way to graph to solve these problems. So I can see right here this is the point 1, -2. So you can write your solution like that, or you could say x equals 1, comma y equals -2. And if you try it, 1 and -2 will solve both of these, right? I can just do this one in my head. 1 minus -2 would be 3 because I'd have a double negative in there. So that would work, and it'll work for the top one too. Okay, so there's my solution. All right, so sometimes you might get no solution. That's when the two lines are parallel. And you might get infinite solutions if the two equations give you the exact same line and all of their points are shared. Okay. All right, so let's move on to the next page and solve a system by substitution. So what you want to do is isolate one variable in one equation, in either equation, in either one you choose, okay? So looking at this example, I'll kind of do this example as I talk about the steps. I can see that the y is already isolated in the first equation, so I don't have any work to do in that isolation phase because y is already equivalent to all of that. Y is isolated, okay? Now I substitute into the other equation. So hey, y is the same as this, so that means anytime there's a y, even in the other equation, I can replace it with x minus 1, the quantity x minus 1, okay? So I'm substituting into the second equation. I'm going to use parentheses just to indicate where I substituted, replacing the y with x minus 1. If you didn't use parentheses here, it's not a big deal, but like if I had a minus there, it would be, because then I'd have to distribute. So this would look the same without parentheses. And then I'll combine these like terms. Okay, I'm going to add 1 to both. Now I'm trying to isolate the x, so I'm adding 1 to both sides. And then I've got 2x equals 8. Divide by 2. And I've got x equals 4. And I'm done. Wait a second. No, I'm not, because that's only the x coordinate. Remember, these are two lines. They're linear equations, so I want to find where they intersect, like on that last problem. And I only got the x coordinate. Still need the y, right? So once you get one of the variables, go back to one of the original problems, one of the original equations, I should say. I'm going to use this one up here. And now I can substitute in 4 for x. And then y equals 3. So there's my solution. So you could write it as the 0.43, or you can write x equals 4, y equals 3. I don't really care. They mean the same thing. Okay? All right, another method. So we did graphing, we did substitution, and now we've got elimination, sometimes called the addition or subtraction method. What you want to do is line up variables, equal signs, and constants. So I'll talk about what that means in the example down below. So you see on this example, my x's are lined up, my y's are lined up, my equal signs are lined up, and the constants are the numbers that are not attached to variables. So everything's already lined up. So I don't have to mess with this one, but if they weren't lined up, I'd want to line everything up. Like, if the bottom equation said 2y plus x, I'd want to flip that around. So that it doesn't have to be alphabetical, but you want both equations lined up in the same way. And then once you do that, you can add or subtract the equations to eliminate one variable. Okay? Now when I'm looking at this, if I were to add these two equations together, I'd have 3x, I'd have negative y, and then I'd have 8. So the variables would not eliminate themselves there. Now what if I subtracted? I'd have 2x minus x would be x, negative 3y minus 2y would be negative 5y. It still wouldn't eliminate. So sometimes, often, you will need to multiply one or both equations so that the variables eliminate. Okay, so instead of just adding these or subtracting them as they are, I want to think, okay, I got to choose. Do I want to eliminate the x's or the y's? You can choose. It doesn't matter. It's up to you. For me here, the x's are easier because I want to get those to be opposites. And I could do that with the y's. I could multiply this by 2 and that by 3, and then I'd have negative 6y and 6y. But it's easier to do the x's, because then I've only got to multiply one of these equations. Okay? So I'm drawing these little arrows, and I'm going to indicate what I'm doing. So what I'm going to do here is multiply the whole bottom equation by negative 2. I'm going to leave the top equation as it is. Okay, but the bottom equation, I'm multiplying not just the x, but all three terms. So this would give me negative 2x minus 4y equals negative 10. Okay, and now if I were to add these together, I'd be in business, because those x's will eliminate, right? 2x plus negative 2x is nothing at all. And then I add up the rest of it. Okay. I'm forgetting about my steps here. Okay, solve the equation that has, so now I've got an equation with one variable. I want to solve that equation with one variable. Well, this is pretty easy, because all I have to do is divide by negative 7 on both sides, and then y equals 1. So that's part of my answer. Okay, substitute into any equation with both variables. So you can always use one of the original equations, but you can actually use any equation that has x and y in it. Okay, so I'm going to use I'll use this one here, since I know what y is. So I'm actually going to finish this with substitution. I know y is 1, so I'm going to replace the y with 1 like so. and then subtract 2, and x equals 3. Oops, I'm off screen there a little bit. Okay. If both variables eliminate and you are left with a true equation, then there are infinite solutions. So sometimes the x and the y, when you do this step, will both cancel out. Okay, so let's say I did this step, x's and y's both canceled out, and I got -7 equals -7. Well, that's a true statement. But if I got -7 equals 4, that would be a false statement. And when that happens, if both variables eliminate and you get a false equation, then there are no solutions. Okay, all right, let's try some more of these on the next page. Okay, so solve by elimination. So, okay, I'm thinking I can eliminate the x's or the y's. It doesn't really matter. They're going to be the same amount of work. Well, if I double the top equation and I leave the bottom equation alone, remember to double all of the pieces. Oops. Just recopying that bottom one. Then when I add these together, hey, the x's will eliminate, but oh, the y's will as well, and even the constants will. So I end up with 0 equals 0. So no more variables, but I'm thinking, is that a true statement? Well, 0 does equal 0. That's true. So that means that this has infinite solutions. Okay. All right, let's try the next one. So I'm thinking, what's easier to eliminate? They're both going to take about the same amount of work. I think I'm going to go for the y's just because they're smaller numbers. So I'm thinking, okay, if I wanted to eliminate these, well, what if I got them both to be, if I want them to be opposites, what about if I had this be -6y and +6y? I could achieve that by multiplying the top equation by 2. That would give me -6y. And the bottom equation by 3. That would give me +6y, okay? And then I got to do the same thing to all the terms. So on top, I've got 10x minus 6y equals -2. On bottom, I've got 9x, because I'm multiplying by 3, plus 6y equals 21, okay? So now when I add these together, those will eliminate. Let's see what I got left. 19x equals 19. That worked out nicely, because that means x will equal 1. And I can go back and substitute into one of the original equations now to get, since I have x, I can use that to find y. So I'll substitute into that second equation, but it'll work the same either equation you use. Okay, I'll subtract 3. And then I'm going to divide by 2, and y will equal 2. Okay. All right. And then we've got a word problem. It's a very common type where we've got some coins and some amount of money. Okay. Bilbo has 6 more quarters than dimes for a total of $3.95. And we want to know, how many of each does he have? Okay. So what I'm going to do is I'm going to write 2 different equations. So let's let D be the number of dimes and Q be the number of quarters. Okay. Let's write an equation for the money, okay? So I know that each dime is worth 10 cents. Okay, so I'm going to write 10 cents that way. So 10 cents for each dime, okay? And then I'm going to get 25 cents for each quarter. And then I know my total amount of money is going to come out to $3.95. Okay. All right. So we need a second equation. We can't actually solve this for dimes and quarters, but we still haven't used this piece of info. we've only really used what the coins are worth. So I'm now going to write an equation that's dealing with the number of each. So I've got 6 more quarters. So I'm thinking, okay, I've got more quarters. So I could take the number of quarters and minus 6 to get the number of dimes. Or you can take the number of dimes and add 6 to it to get the number of quarters. People often mix that up because they see 6 more quarters, so they say quarters plus 6. But that would mean you'd have more dimes. We've got more quarters, right? So either that or D equals Q minus 6, something like that, okay? And now I can actually solve these if I use these together. So it doesn't say what method to use. For me, I'm going to use substitution. I think that's the easiest in most cases. That's the one I use the most often. And here, the Q is already isolated over here. So that means I can replace the Q over here with D plus 6. Okay, so let's try that out. Okay, so I've got it down to this, and now I've got an equation that only has one variable. Okay, so I want to solve this. I'm first going to get rid of the parentheses by distributing the 0.25. And I'm thinking, oh, 0.25 times 6 quarters would be $1.50, right? So this must be 1.50. Okay, I'm going to combine my like terms, which are those two. That would give me 0.35 D. Okay, and now we're trying to get D by itself, so let's subtract 1.50. Gives me 2.45 on the right side. Okay, and then let's divide by 0.35. Hopefully I got a nice round number. Use my calculator there. And I did. If I got 7.3 dimes, then I'd be worried, but it came out to an even 7. So I'm pretty confident. I'm feeling good about that. So that's my number of dimes. Still need the number of quarters, but then, hey, I can go back up here. If I have 7 dimes, I just add 6 to that to get the quarters. So that would mean 13 quarters. Okay, 7 dimes, 13 quarters. You can try it out. Works with both pieces of information. Okay. Okay, so now we're going to solve a system with 3 variables. So here we've got a system, it's got 3 equations and 3 variables. And just like before, you want this to be lined up. This one's already lined up. The x's, the y's, the z's, the equal signs, and the constants. If you have to shuffle some of the equations around to get them lined up, go ahead and do that first. Okay? And this might be a little bit intimidating, but it's really the same process as we were using when we were eliminating with the smaller system with 2 equations and 2 variables. So what you want to do is you want to pick any two equations and eliminate one variable. Okay? So I'm just going to pick the top 2 equations. I'm also going to label these. You don't have to do this, but it makes it a lot easier. I'm going to call these equations A, B, and C, just so I can keep track of what I'm doing. So first I'm going to use equations A and B. And I'm deciding I'm going to eliminate the x's. Okay, so I'm just going to circle that so I remember which ones I'm going to eliminate. Okay, so down here I'm going to pick out equation A and equation B, and I'm thinking, well, if I added these or subtracted them right now, the x's wouldn't eliminate. But if I multiplied the top equation by 2, then the x's would be opposites, okay? So I'm going to make myself a little note over here. I'm having equation A multiplied by 2, okay? So I'm going to multiply all 4 terms by 2. So that would be negative 2x plus 2y plus 4z equals 14. Okay, so there's my equation A doubled, right? I'm going to leave equation B alone because I can see now that the x's are going to eliminate. Okay, and again, you could eliminate a different variable. I just happen to choose the x's. So now I'm looking at those and I'm thinking, okay, if I add these together now, the x's are gone. Let's see what I got left. 5y plus 5z equals 15. Okay, so now I've created this beautiful new equation that only has two variables. I'm going to give this one a name. I've already used a, b, and c, so I'm going to call this equation d. Okay? All right, so what I want to do now, I'm just going to leave that alone for now. I'm going to do the same thing except with two different equations. I'm going to pick two different, so I don't want to use A and B. I could use A and C or B and C. I need to use another combo than I used over here. So with a different combo, I'm going to eliminate the same variable. Okay? And I really think it helps to label what you're doing. That way, if you make, it's really easy to make one little mistake on these, and it's very hard to figure out what the mistake is. Makes it a lot easier if you can track back to see what you were doing in the different steps. Okay, so I could use B and C, but I'm looking at the x's. That would to me it seems easier to use A and C because I can see, all right, I don't have to do as much multiplication. I can multiply equation A by -3, then those would be opposites. If you use B and C, then you got to multiply both by something. That's okay, you can do that if you wanted. I'm going to use A and C, and I'm thinking, all right, I've got to multiply equation A by -3 in order to get the x's to be opposites. So let's think, equation A times -3, multiplying everything by -3. So y times -3 would be -3y. 2z times -3 would be -6z, and 7 times -3 would be -21. Okay, I'm leaving equation C alone. Okay, then I'll add these together. Those eliminate again, and I've got -7y minus 5z equals -17. Okay, and I've got yet another beautiful equation here, and I'll call this equation E. I've already used up A through D, so okay. So now this says solve the system. So the system, what I mean by that, I'm going to create a new system with my two new variables, okay? So here, I'll say, just make a little note here, using D and E. So I'm going to put these two together, okay? So let me just line those up. And so it says solve the system. You can use any method you want. You could use elimination or substitution. You could even graph the lines if you wanted to. Okay. Or maybe that's what I was meaning here for my blank. Solve the system using the two new equations, I think is what I actually meant there. But yeah, anyways, I'm putting D and E together here. So let's go ahead and do that. And looking at these, I'm going to use elimination because I see that these z's are already opposites. So I'm just going to use these as they are. I don't need to multiply them by anything. They're already ready to go for addition. So let me, and it's so easy to accidentally copy just one sign down wrong or one number down wrong, and then it's going to ruin your final answer. And it's really hard to know if you made a mistake. So I'm trying to be really careful here. Okay, so let's add this together. No more z's. Okay, now I can divide by -2. Or you could multiply it by, well, yeah, let's divide by -2. You can multiply by -1/2, I guess. And I've got y equals 1. Okay, so I am on my way. All right. Now, you know, what I want to do is I'm thinking, how can I move forward from this? Well, let's just forget about everything above this. I could solve this system, right? because I've already got the y, now I can go back to one of the equations that has both variables. So I'll use equation D. I'll maybe use this one up here. I don't have to do anything to it except substitute in my y value, which is 1. Okay, so then I've got 5 plus 5z equals 15. I'll subtract 5. And then divide by 5, and z equals 2. Okay? So once you have solved for two of the variables, substitute both of those variables into one of the original equations. And then I can solve for the third one. So I'm going back to either equation A, B, or C. Choose whichever one you want. I'm just going to use A. Okay? But I'm going to go back and use A here and substitute in, let's see, I don't have X yet, but I have Y and Z. So Y was 1, Z is 2. Okay, I can subtract 5. Okay, and then I can multiply or divide by -1. And there is my x value. So you can leave your answer in this format if you like. You can also write this as an ordered triple if you like. So it's kind of like an xy pair, except it's 3 of them, right? So I could write this as -2, 1, 2. And that's fine either way. Doesn't matter. And there is your solution. Okay, so let's try another. These can be a pain, but you just have to be methodical and careful. Lots of opportunity for little mistakes. Okay, so I'm going to try this one out then. All right, so first thing I'm going to do is label them A, B, and C. And I'm thinking what would be the easiest to eliminate? Well, the z's have the smallest numbers. I think I'm going to go for the z's. So just to remind myself what I'm doing, going for those. And let's see, I'll use, actually, if you look at A and C, they're ready to go because the z's are already opposite. So let's do that first. I can just leave them as they are. Those eliminate. Now I've got 4x plus 5y equals 0. Okay, all right, that's one of my new equations. I'll leave that alone. Now I'm going to repeat the process with the z's. I think I'm going to use b and c because then I just have to multiply b by 2. So I'll do that down here. Make myself a little note what I'm doing with equation b. So 8x times 2, 16x. Negative 9y times 2 would be negative 18y. Negative 2z equals 10. Okay, leaving equation C alone. Okay, and let's eliminate again here. I've got 19x minus 14y equals 0. Okay, and there's equation E. All right, so now I'm going to make a system out of these two new equations. So maybe I'll kind of do this just to keep track of what I'm doing. Here's my two new equations. And let's see, I want to eliminate something. Well, actually, you don't need to eliminate because we could also do substitution. And actually, looking at these two equations, it wouldn't be that easy to eliminate for the x's or the y's. So I think I might actually do substitution instead. So I'm going to isolate one of the variables. I'll use the top equation. So let's see. I'm going to subtract 4x from both sides. So 5y is going to equal negative 4x. And then I'm going to divide by 5 to isolate the y. Okay, so then y is going to equal negative 4/5 x. Okay, and now I've got something that I can substitute into the other equation for y, right? So where this y is right here, okay, and this is going to be a little bit ugly because we got some fractions to deal with, but that happens sometimes in life, so let's just go ahead and try it out. So first, I'm checking 14 times 4 is going to be 56. I'm thinking this is 14 over 1 times 4/5, right? So I'd multiply 14 times the top number. And a negative times a negative is going to be positive. So I've got 56 over 5. Okay. All right. And now let's combine these. So you can think of 19x as 19 over 1 times x, right? So I want a common denominator, so let's go ahead and do that. So 5 times 19 is 95, and then 5 times 1 is 5. Okay, now I can add these together because I've got a common denominator. So let's see, 95 plus 56 is 151. Okay, and now what I want to do is isolate the x. So what I like to do on a problem like this to isolate the x is I just multiply by the reciprocal of the fraction, because those two fractions multiplied together equal 1, and that would leave me with just x over there. Okay, so I'll multiply both sides by that. And I could tell that this was going to happen because I had the 0 on the right side. But 0 times anything equals 0. But I thought it might be a good opportunity to review how to deal with fractions. Okay. All right, so got my x value. Took me a little while. And now let's go back and get the y to go with it. So I'm going to use equation D up here. So 4 times 0 plus 5y equals 0. So 0 plus 5y is just 0. Divide by 5, or you can think 5 times what equals 0. And y is also 0. Okay? And now that means I'm going to go back to one of the original equations. I'll just use equation A. And I'll plug in the two variables I know. So this is x. I know x is 0. Plus y. Y is also 0. Minus 2z equals 10. So negative 2z equals 10. And that means z is going to equal negative 5. Really helps, I think, oh, I'm off screen. On problems like this, actually all algebra problems, I like to put the little lines through my z's, because otherwise 2z can get confusing. It might look like 22, right? So I like to put lines through the z's and not through the 2's, and then you can tell the difference. So if you could do that too, that would be great. Okay, and that's it. See you next time.